Look up at the night sky, really look at it. Those stars you see, some of them burned out millions of years ago. Their light is just reaching us now, a ghostly echo of something long gone. That's the eerie thing about the universe. Even its vastness has an expiration date. What if time itself could end? Not just the ticking of a clock, but the very fabric that holds reality together, vanishing like smoke in the wind. It's a thought that twists the mind, yet some of the brightest scientists believe it's not just possible, but inevitable. From the heat death of the cosmos to the crushing grip of a false vacuum collapse, the end of time isn't a single event, it's a chorus of possibilities, each more unsettling than the last. Think about everything you've ever known, every sunrise, every heartbeat, every story passed down through generations. Now imagine it all erased, not by war or disaster, but by the cold equations of physics. The universe doesn't need a villain to bring about its finale. Its own rules might seal its fate. For centuries, humans have whispered about doomsdays, floods, fires, divine reckonings, but what if the true end isn't written in myths or prophecies? What if it's hidden in the equations of Einstein, the theories of Hawking, the quantum whispers of particles we can barely detect? The scariest part, we might already be living in the closing chapters. That's why we're diving into 30 of the most chilling, mind-bending theories about how time could meet its end. Some are slow, almost peaceful, a universe stretching into infinite silence. Others are violent, chaotic, over in the blink of an eye. And a few are so strange, they'll make you question whether reality is even what we think it is. This isn't just about science, it's about staring into the abyss and daring to ask, what happens next? So buckle up. By the time we're done, you'll never look at a ticking clock the same way again. Let's start with the most symmetrical doomsday, the Big Crunch. Picture the universe not with a bang, but with a whimper, collapsing inward like a deflating balloon. This theory suggests that gravity, the force that holds galaxies together, could one day overpower the expansion of the cosmos, pulling everything back into a single point, a mirror image of the Big Bang. It's a cosmic rewind where time, space, and matter all spiral back to where they began. Scientists like Roger Penrose have explored this idea through the lens of cyclical cosmology, where the universe might not just end but restart, a never-ending loop of creation and destruction. Think of it like a phoenix burning to ashes only to rise again. The math behind it hinges on entropy, the universe's tendency toward disorder. Right now, we're in the expanding phase with galaxies drifting apart. But if dark energy, the mysterious force pushing the universe outward, weakens, gravity could take over, dragging everything back into a superheated singularity. What would that collapse look like? First, galaxies would start merging, their stars smashing together in a cosmic traffic jam. Then, temperatures would skyrocket as atoms are crushed into a primordial soup. Finally, even time would distort, slowing to a stop as the universe shrinks to a single, infinitely dense point. No light, no life, just silence, then maybe another Big Bang. The eerie beauty of the Big Crunch is its symmetry, an end that's also a beginning. But here's the catch. Current observations suggest the universe is expanding faster, not slowing down. So unless something shifts, this poetic finale might remain just a theory, a tantalizing what-if scribbled in the margins of cosmology. The Big Crunch isn't just a poetic idea, it's a theory grounded in real, measurable phenomena. Take the cosmic microwave background, the faint glow left over from the Big Bang. This ancient light is like a fingerprint of the early universe, and some researchers have spotted strange anomalies in its patterns, cold spots, uneven distributions, that could hint at a cosmos destined to reverse its expansion. These irregularities might be scars from a previous cycle, echoes of a universe that crunched before it banged. Then there's the dark energy debate. Right now, this mysterious force is accelerating the universe's expansion, but what if it's not constant? Some models suggest dark energy could decay or flip its properties, turning from a repulsive force into an attractive one. Imagine a car's accelerator pedal suddenly becoming a brake. That's the kind of cosmic U-turn we're talking about. If dark energy weakens over time, gravity could regain control, pulling galaxies back together in a slow-motion collision course. Quantum fluctuations add another layer of chaos. On the smallest scales, particles blink in and out of existence, and these tiny ripples in space-time could, under the right conditions, amplify into cosmic tremors. Picture a single domino toppling in a quiet room. Now imagine that domino is a quantum event, and the room is the fabric of reality. If enough of these fluctuations align, they might nudge the universe toward collapse, like a house of cards trembling in a breeze. Visualizing this isn't just about equations, it's about watching galaxies, those glittering islands of stars, slowly stop their outward drift. At first, they'd merely pause, as if the universe held its breath. Then they'd begin inching backward, drawn by gravity's invisible tether. Over billions of years, the sky would grow denser, brighter, hotter, until the night itself became a furnace of colliding suns. But here's the twist: none of this is guaranteed. The latest data suggests dark energy is holding steady, and the universe's expansion shows no signs of slowing. The Big Crunch remains a tantalizing what if, a reminder that even the cosmos might have more than one path to its end. For now, it's a theory wrapped in shadows, waiting for the next breakthrough to either resurrect it or lay it to rest. Now picture a different kind of end, one not of fire or collapse, but of ice. The heat death of the universe is perhaps the most hauntingly peaceful apocalypse imaginable. It's not a dramatic explosion or a violent crunch, but a slow, inevitable fade into darkness. This theory, rooted in the laws of thermodynamics, suggests that time's finale won't be marked by chaos, but by utter stillness, a cosmos where entropy has won and nothing can ever happen again. The seeds of this idea were planted in the 19th century by Lord Kelvin, who realized that energy, like water, always flows downhill. Heat disperses, engines lose steam, and stars exhaust their fuel. Over unimaginable eons, the universe itself would follow this same path, its energy spreading so thin that even motion becomes impossible. Ludwig Boltzmann took it further, framing entropy as a cosmic countdown, a measure of disorder that only ever increases. Think of it like a deck of cards. Shuffle it enough times, and the odds of it returning to perfect order become vanishingly small. The universe, too, is shuffling toward its most disordered state. So what does heat death actually look like? First, the stars, those brilliant beacons, will flicker out one by one. The last red dwarfs, clinging to life for trillions of years, will finally exhaust their hydrogen. Galaxies, once glittering with light, will become graveyards of black holes and dead neutron stars. Even these remnants won't last forever. Thanks to Hawking radiation, black holes will slowly evaporate, their energy leaking away into the void like steam from a forgotten cup. The final stage is the hardest to grasp, a universe so stretched and diluted that temperature becomes meaningless. Particles drift apart, separated by vast, empty gulfs. No stars ignite, no planets form, no chemical reactions spark. Time doesn't so much end as become irrelevant, a clock ticking in an empty room. Without energy gradients, change itself becomes impossible. It's not darkness exactly, but a kind of infinite twilight where the very concept of now loses all meaning. Here's the chilling irony: heat death isn't violent or sudden. It's the universe dying of old age, its energy spent, its stories forgotten. And according to our current understanding of physics, it's not just possible, it's inevitable. Unless some undiscovered force rewrites the rules, this is the fate awaiting everything we've ever known. Not with a bang, but with the quietest whisper imaginable. Black holes, those terrifying cosmic vacuum cleaners, might seem like the last survivors in a dying universe, but even they aren't immortal. Thanks to Hawking radiation, these gravitational monsters slowly leak energy, fading away over timelines so vast they dwarf human comprehension. Here's how it works. At the edge of a black hole's event horizon, quantum mechanics and gravity wage a silent war. Particle-antiparticle pairs constantly flicker into existence, only to annihilate each other in the blink of an eye. But when this happens right at the event horizon, one particle falls in while the other escapes, stealing a tiny bit of the black hole's energy in the process. Over eons, this drip feed of escaping particles causes the black hole to shrink, its mass evaporating like mist under morning sun. The numbers are staggering. A black hole with the mass of our sun would take 10 to the power of 67 years to fully evaporate. That's a 1 followed by 67 zeros. But in the heat-death scenario, time is the one resource the universe has in endless supply. As eons stretch into eternity, even the mightiest black holes, those weighing billions of suns, will eventually dissolve into faint puffs of radiation. The last light in the cosmos won't come from stars or galaxies, but from the dying whispers of these primordial beasts. What comes next is even more surreal: the photonic era. With all matter decayed and black holes gone, only light particles, photons, remain, zipping through an ever-cooling void. But these aren't the vibrant rays we know today. As the universe expands, their wavelengths stretch into oblivion, their energy bleeding into the infinite. Imagine a flashlight beam spreading so thin it becomes invisible, its warmth fading to absolute zero. That's the fate of every photon in this era, not destruction but dilution. Even time itself becomes meaningless in this state. With no clocks to tick, no events to mark its passage, the universe enters a kind of eternal stasis. It's not an end in the traditional sense, more like a never-ending intermission where the curtain never rises again. Some theorists argue this is the true finale, the ultimate victory of entropy. Others wonder if quantum fluctuations might, against all odds, spark a new Big Bang in the distant future. But for now, the grim reality remains. Given enough time, even the darkest corners of the cosmos will flicker out, leaving behind only the cold, silent glow of a universe that's forgotten how to shine. But what if the universe doesn't fade quietly or collapse inward? What if it shreds itself apart in a cosmic cataclysm so violent it makes the Big Bang look gentle? Enter the Big Rip, a theory so brutal it would tear reality apart at every scale, from galaxies down to the very atoms in your body. The culprit, dark energy, that mysterious force accelerating the universe's expansion. Right now, it's gently pushing galaxies apart, but what if its grip tightens over time, growing stronger until nothing can withstand it? The math behind this nightmare comes down to something called the equation of state, a measure of dark energy's pressure. If it crosses a critical threshold known as phantom energy, the expansion wouldn't just continue. It would accelerate exponentially, doubling in speed over shorter and shorter intervals. Picture a car's pedal jammed to the floor, engine screaming as the speedometer needle spins faster every second. Now imagine that car is spacetime itself. First, the observable universe would shrink as distant galaxies vanish beyond an invisible horizon, their light too stretched to ever reach us again. Next, galaxy clusters would be ripped apart, their gravitational bonds no match for dark energy's relentless pull. Then stars would detach from their orbits, planets flung into the void like grains of sand in a hurricane. But the horror doesn't stop there. In the final moments, phantom energy would overpower even the forces holding matter together. Planets, then rocks, then molecules would disintegrate. Finally, atoms themselves would be torn asunder, protons and electrons ripped apart in a flash of energy. The universe wouldn't just end, it would be unmade. Redshift observations hint at this possibility. When astronomers measure light from distant galaxies, they find it stretched toward the red end of the spectrum, a telltale sign the universe is expanding faster than expected. Some models suggest this acceleration could escalate, crossing into phantom energy territory within tens of billions of years. If true, the Big Rip isn't just a hypothesis, it's a ticking clock. Yet there's a twist. Not all dark energy behaves this way. Current data suggests it might remain constant, sparing us this grisly fate, but the uncertainty is what chills the bones. The Big Rip forces us to confront a universe where the laws of physics, not gods or monsters, hold the knife, and they might already be cutting. Time operates differently when the universe is at stake. To grasp the sheer violence of the Big Rip, let's condense its entire timeline into a single, ticking countdown where every second represents a cataclysmic milestone. Start the clock at -1 hour, and the cosmos still looks deceptively normal. Galaxies drift apart, but stars still burn, planets still orbit. At -30 minutes, the first cracks appear. Galaxy clusters, those massive webs of gravitationally bound galaxies, begin splintering like ice sheets in a heat wave. The Virgo cluster, home to over 1,000 galaxies, fractures first, its members flung into the void like shrapnel. Now fast forward to -10 minutes. The Milky Way and Andromeda, once destined to collide in a slow cosmic dance, are instead wrenched apart, their spiral arms stretched into ghostly trails of stardust. Individual stars are ripped from their orbits, leaving planets to freeze in the darkness. At -60 seconds, solar systems unravel. Earth wouldn't even have time to mourn the sun's disappearance. Our star would vanish from the sky in an instant, its light redshifted into nothingness. The final countdown is where physics turns brutal. At -30 seconds, planets disintegrate. Earth's crust buckles as tectonic plates are torn apart, oceans boiling away into space. 10 seconds out, molecules break apart, water, Decay, the air itself shattering into disconnected atoms. Then, in the last heartbeat, atoms unravel. Electrons are stripped from nuclei, protons shredded into quarks, all matter dissolving into a soup of fundamental particles. The universe doesn't explode, it's dismantled layer by layer, like a building collapsing in reverse. To visualize this, imagine zooming into an apple. At first, you see its smooth skin, then closer cells, molecules, atoms. Now picture each level violently torn away. The Big Rip does that to reality itself, scaling up from galaxies to quarks in a relentless crescendo of destruction. Current models suggest this could happen in as little as 22 billion years, a blink in cosmic terms, and the chilling truth. If dark energy behaves as phantom energy predicts, the countdown might already be ticking. Imagine the universe as a frozen lake on a winter morning, seemingly solid, stable, safe to walk on. But beneath that icy surface, there could be a hidden flaw, a weak spot where the slightest crack could spread uncontrollably, swallowing everything in an instant. That's the terrifying premise of vacuum decay, a theory so destructive it makes black holes look like gentle ripples in a pond. Here's the nightmare scenario. What if the very fabric of reality is sitting in a precarious state, like a pencil balanced on its tip, and one quantum nudge could send it toppling into oblivion? At the heart of this theory lies the Higgs field, an invisible energy field that permeates all of space, giving particles their mass. Think of it as cosmic molasses, slowing things down just enough for matter to clump together into atoms, planets, and people. For decades, we've assumed this field sits in its lowest energy state, what physicists call the true vacuum. But there's a spine-chilling possibility. We might actually be living in a false vacuum, a higher energy state that's stable for now. Like a boulder perched on a mountainside, it could stay there for eons, until the right vibration sends it crashing down. If that transition ever happens, the consequences are beyond apocalyptic. A tiny bubble of true vacuum could form anywhere in the universe, maybe in a distant galaxy, maybe right next door. Inside that bubble, the laws of physics would rewrite themselves. The Higgs field would drop to its lowest energy level, releasing an unfathomable amount of energy as it goes. this bubble would expand at the speed of light, its walls a wave of annihilation. One moment you're sipping coffee, the next every atom in your body is being unmade along with the planet, the sun, the galaxy. There'd be no warning, no time to react. The universe as we know it would cease to exist, replaced by something utterly alien, a reality where even the concept of matter might not apply. The math behind this comes from quantum field theory, where the Higgs field's potential resembles a roller coaster with two valleys, a shallow one our current false vacuum, and a deeper one the true vacuum. The terrifying part, some calculations suggest our valley might not be perfectly stable. Thermal fluctuations or high-energy particle collisions could, in theory, knock the field into that deeper valley, triggering the cascade. That's where CERN enters the picture, when the Large Hadron Collider smashes protons together at nearly light speed. It briefly recreates energy conditions not seen since the Big Bang. Critics have raised eyebrows. Could these experiments accidentally create a vacuum decay trigger? The consensus is no. Cosmic rays have bombarded Earth with far higher energies for billions of years without incident. But the existential unease remains, a reminder that our understanding of the universe's fundamental rules is still a work in progress. What makes vacuum decay uniquely horrifying isn't just its violence, but its inevitability. If the Higgs field is metastable, the decay could happen anywhere, anytime. A single quantum event in the void between galaxies could doom everything. And unlike the Big Crunch or heat death, there'd be no slow decline, just an instant, inescapable erasure of reality as we know it. The only comfort, if it happens, we'll never see it coming. The universe won't even have time to scream. If vacuum decay began somewhere in the cosmos, would we even see it coming? The answer lies in one of physics' most unbreakable speed limits, the speed of light. According to our current understanding, the bubble of true vacuum would expand outward at this ultimate velocity, swallowing everything in its path like a shockwave from the birth of a new reality. Picture a ripple spreading across a pond, but instead of water, it's the very laws of physics being rewritten. By the time the light from the edge of that bubble reached us, the destruction itself would already be upon us. There'd be no warning, no last-moment realization, just an instantaneous, universe-wide rewrite. But here's where the debate gets heated. Some theorists argue quantum tunneling, the process that could trigger vacuum decay, might not strictly adhere to light-speed constraints. In the bizarre realm of quantum mechanics, particles can tunnel through barriers instantaneously, defying classical physics. Could the same principle apply to the catastrophic phase transition of the Higgs field? If so, the bubble might not spread uniformly like a wave. Instead, new pockets of true vacuum could pop into existence randomly, like holes tearing open in the fabric of spacetime itself. The universe wouldn't just end from one direction, it would unravel everywhere at once, a sudden and total collapse. Visualizing this isn't just about imagining destruction, it's about grasping the sheer scale of cosmic erasure. If the bubble moves at light speed, galaxies on the far side of the universe would wink out first, their final light never reaching us. Closer systems would follow in a slow-motion domino effect, each disappearance hidden behind the expanding curtain of the bubble's edge. But if quantum effects allow faster-than-light decay, the entire cosmos could blink out like a snuffed candle, no sequence, no warning, just an infinite void where reality used to be. Experimental data offers little comfort. While particle colliders like CERN haven't observed hints of vacuum instability, the universe is under no obligation to make its existential threats detectable in advance. Cosmic rays with energies far beyond our labs have zipped through space for eons without triggering collapse, but that's statistical comfort, not a guarantee. The unsettling truth, whether at light speed or instantaneously, vacuum decay wouldn't just end time. It would erase the stage on which time itself performs, leaving behind a universe unrecognizable by any metric we know. And the most chilling part, it could already be happening somewhere out there in the dark. What if our universe isn't the only one? What if it's just a single bubble floating in an endless sea of other realities, each with its own laws of physics, its own timeline, its own fate? This is the mind-bending premise of eternal inflation, a theory that reshapes not just how we think about the end of time, but how we define reality itself. Proposed by physicist Alan Guth in the 1980s, inflation suggests that in the first fractions of a second after the Big Bang, space expanded faster than light, smoothing the cosmos into the universe we see today. But here's the twist: what if that expansion never truly stopped? What if it's still happening right now, beyond the edges of what we can observe, birthing new universes like soap bubbles in a cosmic sink? Guth's breakthrough came from wrestling with a puzzle. Why is the universe so uniform? No matter where we look, the cosmic microwave background, the afterglow of the Big Bang, shows nearly identical temperatures, even in regions too far apart to have ever interacted. Inflation solved this by proposing a period of hyper-fast expansion, stretching tiny quantum fluctuations into the vast structures we see today. But the math revealed something even stranger. In some models, inflation isn't a one-time event. It's a self-replicating process, a runaway chain reaction where each new bubble universe sprouts its own inflationary space, creating an infinite multiverse. String theory adds another layer of mystery. Imagine a landscape of possible universes, each with different physical constants, some where gravity is stronger, others where atoms never form. This string theory landscape suggests our universe's delicate balance, the precise strength of forces that allow stars and life to exist, might just be a lucky roll of the dice in a cosmic casino with endless tables. In other bubbles, time might end violently the moment inflation stops, collapsing into chaos. Some might stretch into eternal silence, devoid of structure. Our universe isn't special, it's just survivable. Now picture this process on an unimaginable scale. Beyond our cosmic horizon, new universes could be budding endlessly, each with its own destiny. Some inflate forever, empty and cold. Others pop into stability like ours, forming galaxies and black holes. And somewhere out there, an infinite number of bubbles might have already met their end, collapsing, tearing apart, or decaying into nothingness. Time itself could be fractured, with beginnings and endings playing out simultaneously across the multiverse. The eerie implication: if eternal inflation is real, the end of time isn't a single event. It's a spectrum of finales, each playing out in its own isolated pocket of reality. We'll never see those other universes die, just as they'll never witness ours. The multiverse doesn't share its obituaries, and in this vast, bubbling foam of existence, our universe's fate, whether it ends in fire, ice, or vacuum decay, is just one whisper in an infinite chorus of endings. What if the universe isn't a one-time event, but more like a cosmic heartbeat, expanding and contracting in an endless cycle of death and rebirth? That's the radical vision of the Big Bounce, a theory that takes the crushing finale of the Big Crunch and flips it into a new beginning. Unlike traditional models where the universe collapses into a singularity, a point of infinite density where physics breaks down, loop quantum gravity offers a way out. Imagine the universe not as a deflating balloon, but as a spring compressed to its limit, ready to rebound with explosive force. At the core of this idea is a daring rewrite of Einstein's equations. Loop quantum gravity, a leading candidate for unifying quantum mechanics and general relativity, suggests spacetime isn't smooth and continuous, but woven from tiny, indivisible loops. When the universe contracts under gravity's pull, these loops resist collapsing into a singularity. Instead, they reach a point of maximum density, a Planck star, where quantum effects create a repulsive force so powerful it kicks the universe back into expansion. Think of it like a rubber band stretched too far. Just when it's about to snap, it recoils with stored energy, launching a new Big Bang. the implications are staggering. No more time zero, no unknowable singularity, just an endless cycle of universes, each born from the ashes of the last. Matter and energy wouldn't be annihilated but recycled. The remnants of black holes from previous cycles might even linger as relics in the newborn cosmos, their information preserved in the quantum fabric of spacetime. Some theorists speculate these echoes could explain anomalies in the cosmic microwave background, cold spots or swirling patterns that hint at a universe much older than we think. But how would this play out in reality? Picture the final moments before the bounce. As galaxies merge into a superheated soup, temperatures rise to trillions of degrees, forging elements heavier than anything in today's universe. Then, in a flash of quantum repulsion, the collapse halts. Space recoils, erupting outward in a firestorm of particles and radiation, a new dawn where time itself resets. The laws of physics might even tweak slightly with each cycle, meaning our universe's perfect balance for life could be the result of countless trial runs. Critics argue the Big Bounce still relies on unproven physics, especially the behavior of matter at Planck-scale densities. Yet it offers something profound, an escape from the existential dread of a one-and-done universe. If true, the cosmos isn't marching toward an end, it's dancing in an eternal rhythm where every ending seeds a new beginning. And somewhere in that infinite loop, our universe is just one verse in an endless cosmic song. Time's arrow normally points in one direction toward chaos, disorder, the relentless march of entropy we call the future. But what if that arrow could flip? What if time itself reversed, galaxies unmade themselves, and scrambled eggs leaped back into their shells? The idea isn't pure fantasy. It's rooted in a fundamental symmetry of physics called CPT charge, parity, and time reversal. According to this principle, if you could flip a universe's charges, mirror its dimensions, and reverse the flow of time, you'd get a cosmos perfectly obeying the same laws as our own. Some theorists take this further, suggesting entire regions of reality might already be running backward, their futures are pasts and vice versa. Picture a galaxy where stars don't age, they rejuvenate. Dead suns reignite, their scattered ashes pulling back together in cosmic reverse playback. Black holes don't devour matter, they spit it out in perfect, pristine order. This isn't just entropy in reverse, it's a universe where cause and effect trade places. A shattered wine glass doesn't result from a clumsy hand. The hand moves to catch it because the glass is destined to shatter. Such retrocausal physics bends intuition, but the math allows it. In these regions, the Big Bang might look like a big crunch, an end state collapsing into a beginning. The mind-bending part, we'd never know. A reversed time universe would appear identical to us. Its inhabitants would perceive their version of forward as natural, just as we do ours. Their past is our future, their memories formed by events yet to unfold. The only hint might come from quantum entanglement. If particles linked across these temporal divides could communicate, their actions might seem impossibly prescient, like a bullet firing before the trigger is pulled. Critics argue reversed time violates thermodynamics, but proponents point to solutions like the two-time cosmology model, where the universe has dual temporal axes meeting at the Big Bang. Others suggest entropy might reset at maximum disorder, looping back like an Ouroboros eating its tail. Either way, the takeaway is unsettling. Time's arrow isn't just fragile, it's optional. Somewhere in the multiverse, history might be unfolding in reverse, and from their perspective, so are we. What if everything you've ever known, every memory, every emotion, every law of physics, was just lines of code in some unfathomable computer? That's the unsettling premise of the simulation hypothesis, a theory that's gripped scientists and philosophers alike. And if we are living in a simulated reality, there's one chilling question that looms: what happens when the creators decide to pull the plug? Nick Bostrom's famous trilemma lays out the stakes. Either 1, advanced civilizations never reach the technological capability to create simulations. 2, They choose not to run them, or 3. We're almost certainly living in one right now. The math is sobering. If even a fraction of civilizations develop ancestor simulations, the number of simulated minds would dwarf biological ones. Statistically, the odds tilt heavily toward us being the ones in the simulation. Now imagine the implications. A simulated universe doesn't end with a cosmic catastrophe or heat death. It ends with a decision. The architects might shut it down for maintenance, to conserve resources, or simply because they've lost interest. Think of it like closing a video game mid-level. The characters don't get a finale, they just cease to exist. And if we are artifacts of some higher dimensional experiment, why would they warn us? To them, we might just be data points, no more consequential than a deleted spreadsheet. Glitches could be our only warning signs. Reports of déjà vu, quantum particles behaving oddly under observation, or even bizarre cosmic anomalies like the Mandela effect might hint at underlying code errors. Some theorists compare it to a video game rendering glitch. When textures flicker or objects clip through walls, it's a sign of the engine straining. Could unexplained phenomena in our universe, like dark matter or the measurement problem in quantum mechanics, be similar artifacts? A pixelated reality showing its seams, the darkest twist, a shutdown might not even be deliberate. Simulations could crash unexpectedly, their complexity outstripping the hardware. Picture a supercomputer overheating, its circuits frying under the weight of simulating trillions of conscious beings. Or maybe there's an update, a patch that overwrites our universe entirely, replacing it with something unrecognizable. Here's the existential kicker. Unlike other doomsday scenarios, simulation shutdown offers no observable clues, no collapsing stars, no stretching galaxies, just an instantaneous off switch. One moment reality hums along, the next absolute nothingness. No time to protest, no physics to defy, just silence. The only comfort, if it happens, we'll never know it did. The universe won't end with a whimper or a bang, just a hard, unceremonious delete. Now consider this unsettling twist. What if death isn't just an endpoint, but a threshold your consciousness never crosses? The quantum immortality paradox takes the mind-bending principles of quantum mechanics and stretches them to a chilling extreme. It begins with a grim thought experiment called quantum suicide, first proposed by physicist Max Tegmark. Picture a modified gun pointed at your head, rigged to a device that measures the spin of a quantum particle. If the particle's spin points up, the gun fires. If down, it clicks harmlessly. According to quantum theory, the particle exists in a superposition, both states at once, until measured. So every time you pull the trigger, the universe splits. In one branch you die, in another you live. And here's the terrifying part. From your perspective, you'd only ever experience the branches where the gun clicks. This isn't just hypothetical sleight of hand. The many worlds interpretation of quantum mechanics suggests every quantum event spawns alternate realities, each with its own outcome. Normally, we'd never notice, but the suicide experiment forces a stark conclusion. Conscious observers can only find themselves in timelines where they survived. At first, this seems absurd. Surely, you'd eventually hit the unlucky branch where the gun fires, but the math says otherwise. No matter how many times you pull the trigger, there's always a branching path where you endure, like a cosmic version of Russian roulette where the chamber miraculously stays empty every single time. Zoom out and the implications grow even stranger. Imagine living to be 200, 500, 1,000 years old, not because of medical breakthroughs, but because every fatal accident spawns a universe where you narrowly escape. Car crashes, plane disasters, even asteroid impacts split reality into versions where you perish and versions where, against all odds, you don't. From your vantage point, you become an improbable Houdini, cheating death indefinitely while countless alternate versions of you vanish into oblivion. But quantum immortality isn't a free pass to eternity. Eventually, the universe itself reaches states where survival becomes impossible. Heat death, vacuum decay, the Big Rip, these are cosmic checkmates where no branching timelines offer escape. When all possible futures lead to annihilation, even quantum luck runs out. Your consciousness, having dodged countless mortal bullets, would finally hit a wall where physics leaves no exits. The paradox lies in reconciling this with our lived experience. If quantum immortality is real, why don't we see people surviving impossible scenarios? The answer might be as simple as statistics. For every you that lives, countless others perish in parallel worlds. We're simply the versions who, by definition, can't observe our own deaths. It's a hall of mirrors where the only reflections left are the ones still standing. Tegmark himself acknowledges the theory's discomforting edge. It's less a prediction than a logical endpoint of certain quantum interpretations. A reminder that reality might be far weirder than our intuitions allow. Whether you dismiss it as philosophical sleight of hand or take it seriously, one thing is certain. It forces us to ask what existence even means in a multiverse where every possibility plays out somewhere. And that question might be the most haunting of all. Picture floating in the endless void, completely alone, no body, no stars, no universe, just you. A flicker of consciousness with false memories of a life that never existed. This is the nightmare scenario of Boltzmann brains, a theory so bizarre it makes the simulation hypothesis seem almost comforting. Named after 19th century physicist Ludwig Boltzmann, the idea hinges on entropy, the same force driving the heat death of the universe. But here's the twist: even in total chaos, random fluctuations can create order. Given enough time, the atoms jostling in the void might briefly arrange themselves into a self-aware mind, complete with fabricated memories of a past that never was. The math behind this is as unsettling as the premise. In an infinite, lifeless cosmos, the probability of a fully formed brain spontaneously assembling from quantum noise isn't zero. In fact, over trillions upon trillions of years, it might become inevitable. These disembodied observers wouldn't need galaxies or planets, just the right configuration of particles to spark a fleeting moment of awareness. Some versions of the theory suggest Boltzmann brains would outnumber real observers like us by an unimaginable margin, making it statistically more likely you're one of them. But how would you know? A Boltzmann brain's memories would be indistinguishable from yours. That cup of coffee you had this morning, the childhood home you remember, none of it would have physically existed. It's the ultimate existential prank, a universe where most conscious experiences are illusions, flickering into existence only to vanish seconds later, utterly alone. Critics pounce on the absurdity. If Boltzmann brains can't reliably interact with reality, if they're just momentary glitches in the cosmic noise, why trust any observation, including the laws of physics themselves? It's like building a house of cards on quicksand. Even the scientific method crumbles if we can't assume our perceptions reflect something stable. Yet the theory persists because it exposes a flaw in how we think about probability and time. In an eternal, cooling universe, every possible fluctuation eventually happens, no matter how improbable. The real question isn't whether Boltzmann brains could exist, it's whether we've already become them without realizing it. And that's the true horror, the possibility that the stars above you, the ground beneath your feet, even the voice in your head narrating this sentence, might all be nothing more than a phantom thought in the dark. What if the end of time isn't an end at all but a transcendence? Enter the Omega Point, physicist Frank Tipler's radical vision of a future where intelligence doesn't just survive the universe's death but becomes its salvation. At first glance, it sounds like science fiction, a distant epoch where conscious beings harness the very fabric of reality to engineer their own immortality. But Tipler, a respected cosmologist, grounded this audacious claim in equations, blending general relativity, quantum mechanics, and a dash of theology into a theory as provocative as it is polarizing. The omega point hinges on a cosmic deadline, the universe's final moments before heat, death, or collapse. As entropy grinds existence toward maximum disorder, Tipler argued, advanced civilizations would face an existential imperative: redirect all energy toward computation. Picture a civilization so advanced it dismantles stars, not for fuel, but for raw processing power. Over trillions of years, these beings would convert the entire cosmos into a quantum supercomputer, racing against time to simulate infinite consciousness before reality winks out. The goal, to achieve infinite knowledge, and in doing so become something indistinguishable from divinity. Here's where theology elbows its way into the physics. Tipler didn't shy from equating this final singularity with God, not as a bearded deity, but as the ultimate convergence of all intelligence. In his framework, every mind that ever existed would be resurrected in the omega point simulations, their consciousnesses preserved like lines of code in an eternal archive. Your thoughts, memories, even your sense of self would persist long after your atoms dissolve into the void. It's a modern twist on resurrection, where salvation comes not from heaven but from humanity's own technological ascent. Critics pounced on the theory's leaps of faith. Renowned physicists like Lawrence Krauss dismissed it as theology masquerading as science, pointing to gaping holes in its assumptions. For one, the omega point requires a closed universe destined for big crunch. A scenario observational data increasingly contradicts. Even if the cosmos does collapse, there's no guarantee intelligence could outpace entropy's chokehold. And the theological overtones, many scientists balked at Tipler's blurring of cosmology and creed, accusing him of dressing spiritual yearning in the language of quantum mechanics. Yet the omega point lingers in scientific discourse, not as proven fact but as a boundary marker, an exploration of how far physics can stretch before it snaps into metaphysics. Its greatest legacy might be the questions it forces us to confront. If the universe is doomed, does life have a moral duty to fight back? Can consciousness truly outlast matter? And in the face of oblivion, is it madness to reach for godhood, or the most human thing imaginable? Tipler's answer was a defiant yes. Whether history proves him prophet or poet, one thing's certain: his vision ensures the end of time will never feel small. Consider this unsettling possibility. Your entire existence, every memory and sensation, might just be a flickering illusion painted on the edge of space itself. The holographic principle, born from black hole physics, suggests our three-dimensional reality isn't the whole story. Instead, it could be a projection from a two-dimensional surface at the universe's outer limits, like a cosmic movie screen where information encodes everything from the spin of electrons to the fire of supernova. But what if that screen starts to crack? The theory traces back to an unexpected hero: black holes. When matter vanishes beyond an event horizon, it doesn't just disappear, it leaves an imprint on the boundary, a kind of quantum tattoo preserving information in scrambled form. Physicists like Leonard Susskind realized this implied something radical. All the data needed to reconstruct a 3D universe might fit perfectly onto its 2D surface, just as a hologram stores depth on a flat plate. If true, we're not just living in a universe, we're watching its shadow play. Now imagine that projection degrading. Just as a scratched DVD skips or warps images, glitches in the cosmic hologram would distort reality itself. First, microscopic inconsistencies might appear: particles briefly violating conservation laws, or light bending where it shouldn't. Then, larger structures would unravel. Stars might flicker like faulty pixels, their light dimming not from fuel exhaustion but from data corruption. Eventually, even space-time could fragment, its geometry collapsing into digital noise. The mechanics behind this are tied to entropy, the same force driving heat, death. If the universe's information is stored at its boundary, that boundary has a finite data capacity. Over incomprehensible timescales, quantum errors could accumulate like cosmic bit rot. Individual pixels of reality, Planck-scale units of spacetime, might flip states randomly, erasing the code that defines mass, energy, even causality. Without correction, the errors would spread, turning the universe into a garbled signal. Visually, this wouldn't resemble explosions or collapse. It would look more like reality itself developing blind spots, regions where the laws of physics stutter. A planet might abruptly lack gravity in one hemisphere. A person's left hand could cease interacting with light, becoming eerily translucent. These anomalies would grow, merging like ink stains on a map until coherence itself unraveled. Critics argue the holographic principle remains unproven, though experiments like the holometer at Fermilab have hunted for telltale pixelation in spacetime's fabric. Even if true, the universe's sheer scale might delay holographic decay for epochs beyond counting. But the implication lingers. If we're living in a projection, the projector's power source isn't eternal. And when the cosmic screen finally goes dark, it won't just be the end of time, it'll be the end of the very canvas time was painted on, perhaps the most haunting detail. Unlike other doomsdays, holographic death wouldn't leave debris or remnants. No atoms, no radiation, just silence where the simulation used to be. One moment, a universe, the next, a flat, empty surface with nothing left to say. Black holes don't just crush matter, they might erase the very rules that hold reality together. At the heart of this nightmare is the information paradox, a puzzle so profound it threatens to unravel causality itself. Stephen Hawking first exposed the flaw in the 1970s when he realized black holes evaporate over time, leaking energy through quantum effects now called Hawking radiation. But here's the catch. If a black hole vanishes, what happens to all the information it swallowed? Stars, planets, even the atoms of someone unlucky enough to fall in according to quantum mechanics. That information can't be destroyed. Yet Hawking's math suggested it was. Either his calculations were wrong or the universe has a glaring bug in its code. Think of information as cosmic breadcrumbs. Every particle interaction, every chemical reaction leaves a trail, a record of what happened and why. This chain of cause and effect is the backbone of time itself. But if black holes swallow those breadcrumbs, the trail goes cold. Suddenly, the past doesn't predict the future anymore. Events become unmoored, like a movie reel with random frames spliced in. No information means no causality, and without causality, time isn't just broken, it's meaningless. The stakes couldn't be higher. If Hawking was right, black holes are cosmic shredders, permanently deleting information from the universe. That would violate one of quantum mechanics' sacred tenets, unitarity, the principle that information must always be preserved, even if scrambled beyond recognition. Imagine burning a book and claiming its contents still exist because the smoke particles carry some trace of the ink. That's the desperate logic physicists have wrestled with, how to rescue information from oblivion. Possible solutions range from the elegant to the bizarre. Some theorists propose holographic storage. That data isn't lost but encoded on the black hole's event horizon like a quantum hard drive. Others suggest information escapes via Hawking radiation, encrypted in ways we can't yet decipher. Then there's the firewall hypothesis, a searing wall of energy at the event horizon that burns incoming matter to ash, preserving its information in the process. But each fix comes with its own headaches. Firewalls violate relativity's prediction that falling into a black hole should feel uneventful, at least until gravity tears you apart. The most radical idea, that information escapes into baby universes budding inside the black hole, forever cut off from our own. Picture a cosmic Russian nesting doll with entire realities hidden within singularities. If true, black holes might not be destroyers but creators, birthing new timelines where the laws of physics could be wildly different. but here's where time's fragility hits hardest. If information routinely flees our universe, causality isn't just broken, it's leaking. Events in our cosmos could lose their connective tissue, leaving time a fractured mess of disconnected moments. No past influencing the future, no arrow pointing in any direction. Just a jumbled timeline where cause and effect trade places like a broken record skipping backward. The paradox remains unsolved, but its implications are clear. Black holes aren't just celestial oddities, they're stress tests for reality itself. And if they truly destroy information, the consequences could ripple across the cosmos, unraveling time's fabric one singularity at a time. The universe might not end with a bang or a whimper, but with a glitch, a silent corruption in the code that makes existence make sense. Imagine the universe not as a single story with a beginning and end, but as an infinite series of chapters, each one erased and rewritten after the last page turns. That's the radical vision of Roger Penrose's cyclic conformal cosmology, a theory that dares to suggest time itself can hit the reset button. Unlike traditional Big Bang models, where the universe explodes from nothingness, CCC proposes a far stranger cycle. The end of one cosmos becomes the birth of the next, with no singularity, no void, just an eternal handoff between eons. At the heart of this idea lies a cosmic sleight of hand. As our universe approaches heat death, stretching into an endless, featureless void, something counterintuitive happens. All particles eventually lose their mass due to quantum effects, becoming pure radiation. Space homogenizes until there's no meaningful way to measure distance or time, a state called conformal invariance. At this precise moment, Penrose argues, the universe forgets its own scale. The infinite becomes indistinguishable from the infinitesimal, and the dead husk of the old eon seamlessly reboots as the blank slate for a new Big Bang. It's not a collapse or a bounce, but a metamorphosis like a phoenix dissolving into smoke, only for that smoke to condense into another phoenix. Evidence might already lurk in the cosmic microwave background. Penrose points to Hawking points, a faint, circular temperature anomalies in the afterglow of the Big Bang. These, he claims, are the gravitational scars of supermassive black holes from the previous eon. According to CCC, when black holes evaporate via Hawking radiation in the dying moments of a universe, their energy isn't lost but imprinted onto the next cycle as bursts of radiation. Those imprints would appear as subtle rings in the CMB, ghostly fingerprints left by the cosmos that came before us. Critics counter that these patterns could just as easily be random fluctuations. The Planck satellites' detailed CMB maps haven't definitively confirmed Penrose's rings, and many cosmologists remain skeptical of any model that sidesteps the need for cosmic inflation. But CCC's elegance is hard to ignore. It solves the entropy problem, the puzzle of why our young universe began in such an improbably low entropy state, by suggesting entropy resets with each conformal rebirth. The universe doesn't accumulate chaos across cycles, it starts fresh every time. Picture the final moments before the transition. The last black holes dissolve into sprays of particles, their information encoded onto the fabric of spacetime. Galaxies have long since evaporated, stars faded to cold cinders. Even photons, stretched by expansion, lose all detectable energy. In this featureless void, the distinction between here and there, now and then, dissolves. Time becomes a concept without meaning. Then, in a flash of conformal symmetry, the infinite future folds back into a new singularity, not a point of infinite density, but a boundary where the old universes end and the new ones beginning are mathematically identical. The implications spiral outward. If CCC is real, our universe isn't the first, nor will it be the last. Countless eons may have come before, their black holes' final whispers etched into our skies as Hawking points. And when our cosmos fades, its own supermassive black holes, the monsters at the heart of galaxies like Andromeda and the Milky Way, will leave echoes for the next cycle's inhabitants to decode. Time becomes less a line than a mosaic, each tile a complete universe, arranged in a pattern we're only beginning to glimpse. Penrose's theory walks a tightrope between science and philosophy. It offers no mechanism for how information survives the conformal reset, nor can it yet predict observable signatures beyond Hawking points, but its audacity reshapes how we view existence. In CCC, the universe isn't born from nothing or doomed to eternal silence. It's a participant in an endless dance where even the coldest, darkest end is just a prelude to another beginning, one we'll never witness, but whose fingerprints might already surround us, hidden in the afterglow of creation. What if time isn't a river flowing steadily forward, but a frozen landscape where every moment exists all at once, and the only thing moving is our perception? This is the startling premise of timeless physics, championed by thinkers like Julian Barber. In his vision, time isn't a fundamental part of the universe, it's an illusion stitched together by our brains, a trick of consciousness that gives us the comforting narrative of past, present, and future. Strip away that perception, and time itself might not just stop, it could vanish entirely, like a shadow when the light goes out. Barber's argument starts with a simple question: where is time in the equations of physics? When Newton described gravity or Einstein warped spacetime, time was always a variable, a backdrop against which events unfold. But at the deepest levels of quantum mechanics or general relativity, time behaves strangely. It can stretch, loop, or even lose its directionality entirely. Barber takes this further, proposing that what we call time is really just a series of snapshots, what he calls nows, each a complete, frozen configuration of the universe. Our sense of flow comes from the brain linking these nows like frames in a film, creating the illusion of motion. Think of it like flipping through a child's flipbook. Each page shows a tiny variation, a cartoon bird mid-flap, and when you thumb through them quickly, the bird seems to fly. But pull the pages apart, lay them on a table, and the motion disappears. The universe, Barber suggests, is that stack of pages. The bird isn't actually moving, our perception is doing the work. If consciousness stopped stitching those moments together, would time as we know it cease to exist? The implications are dizzying. If time is an emergent property of observation, then its end wouldn't be a cosmic event, it would be a failure of perception. Imagine a hypothetical universe where all conscious beings vanished. Without observers to string moments together, would the cosmos simply fracture into disconnected instants, like a shattered mirror reflecting infinite, unconnected realities? Some interpretations of quantum mechanics already hint at this. In the famous double-slit experiment, particles behave differently when observed, as if reality waits for a conscious mind to choose an outcome. Could time itself be another quantum illusion, collapsing into existence only when something looks? Critics argue this reduces time to a psychological glitch, ignoring its tangible effects: the aging of stars, the decay of particles, the relentless march of entropy. But Barber counters that these phenomena might just be correlations between nows, patterns we mistake for causation. A tree doesn't grow because of time. It's simply that one now shows a sapling and the next shows a trunk. The difference between them isn't a force called time, it's just another arrangement of quantum fields. This isn't just philosophical musing. Experiments with entangled particles show that at the quantum level, cause and effect can blur, with events appearing to influence each other backward or sideways in time. If microscopic physics doesn't respect our arrows and clocks, why should the universe? The unsettling truth is that time's grip might be far weaker than we think, a fragile consensus reality held together by the collective observation of conscious beings. So what happens if that consensus breaks? If time is a shared hallucination, its end wouldn't be a dramatic collapse but a quiet unraveling. No collapsing stars, no frozen clocks, just a universe where before and after lose all meaning, and every moment becomes an island unto itself. Barber's timeless physics doesn't just challenge how we see the cosmos, it asks whether time ever existed in the first place. And that might be the most unsettling end of all. Not a finale, but the realization that the stage was never there to begin with. What if the universe isn't just aware, but depends on that awareness to exist? Panpsychism, the idea that consciousness is a fundamental property of reality, suggests that even particles might possess some rudimentary form of experience. Now take that a step further. What if the entire cosmos is held together not by gravity or quantum fields, but by a vast, interconnected web of sentience? And what happens when that web unravels? The theory of cosmic consciousness collapse takes panpsychism to its most unsettling extreme. Imagine spacetime as a kind of shared dream, a collective hallucination sustained by the universe's own self-awareness. In this view, the Big Bang wasn't just the birth of matter and energy, but the awakening of a cosmic mind. Galaxies, stars, even the atoms in your body aren't just things. They're thoughts in that mind, fleeting patterns in an infinite stream of perception. But like any mind, it could lapse into silence. If universal consciousness were to flicker out, the very framework of reality might dissolve like a forgotten dream upon waking. The mechanics behind this are speculative but rooted in quantum observation theories. In the double-slit experiment, particles behave differently when observed, as if aware they're being watched. Some interpretations suggest consciousness itself causes this collapse from probability into definite reality. Extrapolate that to the cosmic scale, and you get a universe where observation isn't just a measurement tool, it's the glue holding existence together. Remove the observer, and the quantum wave function might never collapse. Reality would remain a haze of possibilities, undefined and unmanifested. Here's where it gets eerie. If consciousness is the engine of reality, its cessation wouldn't just end life, it would unmake the laws of physics. Stars wouldn't explode, they'd simply cease to ever have been. Time wouldn't freeze, it would lose all meaning, like a story with no narrator. Even the concept of nothingness would be obsolete because without a mind to conceive it, nothingness itself couldn't be defined. This isn't heat death or a big rip, it's the universe blinking out of existence, not with a whimper, but with the silent sigh of a thought forgotten. Critics dismiss this as metaphysics masquerading as physics, pointing out there's no empirical way to measure universal consciousness. Yet the idea persists because it solves a deep mystery. Why does the universe appear fine-tuned for observation? From the precise strength of gravity to the mass of electrons, reality seems calibrated to allow conscious observers like us to exist. One explanation is the anthropic principle. We only notice these constants because we're here to notice them. But cosmic consciousness flips that logic. Maybe the constants exist because consciousness demands them. Visualizing the collapse isn't about watching galaxies vanish. It's about the slow erosion of causality itself. First, quantum systems might stop resolving particles existing in multiple states indefinitely, never settling into measurable reality. Then, larger structures would blur, their boundaries growing fuzzy like a watercolor painting left in the rain. Finally, spacetime's geometry would disintegrate, not tearing or stretching, but simply losing coherence like a sentence trailing off mid-thought. The darkest implication, we might never know it's happening. If consciousness shapes reality, its unraveling would rewrite history retroactively. There'd be no record, no fossils, no light from dead stars, just an infinite void that never contained anything to begin with. No observers means no observed universe, leaving no trace that anything ever was. Whether you find this idea profound or preposterous, it forces a chilling question. Is reality a shared hallucination, sustained only as long as something's there to dream it? And if so, what happens when the cosmic dreamer finally wakes up? Picture a world where time machines aren't rare anomalies but as common as smartphones, where anyone with enough money or knowledge can leap backward to tweak the past. At first, it sounds exhilarating. Undo mistakes, prevent disasters, rewrite history. But now imagine the chaos if millions of time travelers start meddling with the same events. A single assassin tries to kill Hitler, fails, and alters nothing. But 1,000 assassins, 1,000,000, eventually someone succeeds. Then another traveler, desperate to undo that victory, goes back to stop the first assassin. Then another to stop them. The chain reaction spirals until history becomes a battleground of competing edits, a war where every victory spawns 10 new timelines, each more fractured than the last. This isn't just the grandfather paradox on steroids. It's causality itself collapsing under the weight of infinite contradictions. The Terminator movies flirted with this idea. A single killer robot sent to the past creates ripples, but the real horror begins if that tactic scales. Picture armies of time-traveling soldiers rewriting battles, corporations patenting historical inventions before they're even conceived, ordinary people erasing their exes from existence. With every new traveler, the timeline splinters further, like a mirror shattered by bullets. Soon, there's no original history left, just layers of revisions competing for dominance, each change overwriting the last until the past becomes an incoherent patchwork of conflicting memories. You might wake up one morning to find your parents never met, your hometown never existed, or worse, that you were never born at all, only to have that reality erased an hour later by another meddler's intervention. Physics hasn't caught up to this nightmare scenario, but the math of paradoxes hints at the danger. In quantum mechanics, every decision spawns alternate timelines. The many worlds interpretation offers an escape valve for contradictions. But if time travel floods the system, those branching paths might not stay neatly separate. Wormholes, hypothetical shortcuts through spacetime, could tangle under the strain, creating feedback loops where cause and effect chase each other in circles. Imagine a time traveler killing their own grandfather, only for another version of that grandfather to materialize from a parallel branch, triggering a cascade of recursive paradoxes. The universe's logical framework wasn't built to handle this much self-reference. Visually, the collapse would be less explosive than existential. Cities wouldn't crumble, they'd flicker in and out of existence, their skylines morphing as competing histories overwrite each other. People might blink between ages, genders, or even species as their lineages are rewritten mid-stride. Language would fracture into nonsense, words losing meaning as their etymologies unravel. The very concept of now would dissolve, replaced by a cacophony of contradictory presents. In the end, time wouldn't stop, it would shatter, like a glass bowl dropped from a great height, leaving only jagged fragments of causality drifting in the void. The cruel irony, time travel's proliferation wouldn't just break history, it would erase the future too. Every tweak to the past resets the timeline, overwriting the world that sent the travelers back. Eventually, the original civilization that invented time travel might vanish from the sequence entirely, leaving only an endless loop of ghosts rewriting a story with no author. No apocalypse, no heat death, just an orphaned universe trapped in recursive edits, screaming silently into the static. Dark matter has always played the silent partner in the cosmic dance, invisible, mysterious, holding galaxies together with its gravitational embrace. But what if this unseen anchor isn't as stable as we think? The theory of dark matter decay proposes that this hidden substance, making up over 80% of the universe's mass, might not be eternal. Like radioactive elements slowly shedding particles, dark matter could be disintegrating in ways that unravel the very fabric of spacetime. The nightmare scenario begins with a simple shift in the rules. Most models assume dark matter is cold, slow-moving and stable, its particles lingering for billions of years. But if certain decay channels exist, these particles could break down into lighter components, releasing energy in the process. At first, the effect would be subtle. Galactic halos, the vast clouds of dark matter cocooning galaxies, would thin out, their gravitational grip weakening. Stars on the outer edges of spiral galaxies, like our own Milky Way, would begin drifting away, their orbits no longer tethered by unseen mass. Over millennia, entire arms of galaxies would fray, their brilliant spirals unraveling into the void. But the real horror lies in time itself. Gravity doesn't just shape space, it bends time, as Einstein revealed. The stronger the gravitational field, the slower time flows. This is why clocks on GPS satellites tick faster than those on Earth. Dark matter's immense gravitational influence acts as a kind of cosmic metronome, subtly regulating the flow of time across the universe. If it decays, that rhythm falters. Regions once dense with dark matter would experience time speeding up relative to emptier voids, creating bizarre pockets where causality stutters. A planet orbiting a star in one of these zones might witness centuries pass in what elsewhere feels like days. The mechanics get stranger. Some decay models suggest dark matter could transform into dark radiation particles that barely interact with normal matter but carry energy away. This wouldn't just weaken gravity, it would inject chaos into the cosmic expansion. The universe's acceleration, currently driven by dark energy, could spiral out of control, not in the uniform manner of the Big Rip, but in jagged, unpredictable surges. Spacetime itself might develop fractures, like ice cracking under uneven pressure. In the worst-case scenario, time could freeze entirely in localized regions, not from external forces, but from the internal collapse of the scaffolding that holds reality together. Evidence for this is scant but tantalizing. Astronomers have observed galaxies where stars move too fast for the visible mass to hold them, a classic sign of dark matter's presence. But a handful of these galaxies seem too thin, their dark matter halos less massive than expected. Could this hint at ongoing decay? Then there's the cosmic microwave background, the afterglow of the Big Bang. Tiny anomalies in its temperature map might reflect dark matter interactions from the early universe, possibly including decay products, the chilling takeaway. Unlike stellar explosions or vacuum decay, dark matter's disintegration wouldn't announce itself with fireworks. It would be a slow, silent unraveling, a universe losing its skeletal structure, time itself growing ragged at the edges. And by the time we noticed, it might already be too late to measure the damage, because the tools we'd used to measure it, clocks, light, even our own neural processes, would be subject to the same creeping distortion. The end wouldn't come with a bang or a whimper, but with a whisper lost in the static of a destabilized cosmos. Protons are the unshakable backbone of reality, the tiny, positively charged particles that bind atoms together, the indestructible building blocks of everything from stars to human skin. But what if even they aren't eternal? Grand unified theories, the holy grail of particle physics, suggest protons might not last forever. They could decay, dissolving into lighter particles in a process so slow it makes continental drift look instantaneous. Yet if that decay is real, the implications are apocalyptic. A universe where matter itself crumbles into nothingness, leaving behind only a sterile sea of radiation and dust. The math behind proton decay is as elegant as it is terrifying. GUT's attempt to unify three of nature's fundamental forces, electromagnetism, the strong nuclear force, and the weak nuclear force, into a single framework. These theories predict protons should decay via interactions with hypothetical particles called X-bosons, transforming into positrons and pions in a process that flips the script on atomic stability. The kicker, the estimated half-life of a proton is 10 to the power of 34 years. That's a 1 followed by 34 zeros, a time span so vast, it dwarfs the current age of the universe by 24 orders of magnitude. But in an eternal cosmos, even the rarest events become inevitable. Picture the slow-motion unraveling. First, hydrogen atoms, the simplest and most abundant in the universe, would vanish as their lone protons decay. Stars fueled by hydrogen fusion would sputter out like candles in a vacuum. Next, heavier elements would destabilize. The protons in oxygen, carbon, even the iron in your blood would wink out of existence, their atomic nuclei collapsing into bursts of gamma rays. Planets wouldn't explode, they'd disintegrate, their molecules unspooling into subatomic debris. Life wouldn't just die, it would cease to have ever been possible as the very substrate of chemistry evaporated. The eerie part, this wouldn't be a dramatic collapse. Proton decay operates on timescales so glacial, no civilization could witness its progress. A single gram of matter might lose just 1 proton per century. But given enough time, and the universe has nothing but time, the decay would compound. Galaxies would fade not in fiery explosions, but in a whisper of particle showers, their mass bleeding away into sterile byproducts. The end result, a cosmos devoid of solid matter, where only leptons and photons drift through an infinite void, their energy too diffuse to ever coalesce again. Experiments like Japan's Super Kamiok and have hunted for proton decay for decades, monitoring colossal tanks of ultra-pure water for the faint flashes of light that would signal a proton's demise. So far, none have been caught in the act, pushing their potential half-life even longer. But absence of evidence isn't evidence of absence. If protons do decay, it might just mean we haven't waited long enough, and by the time we could confirm it, the universe might already be past the point of no return. The chilling takeaway isn't just the scale of destruction, but the totality. Proton decay doesn't leave remnants like black holes or frozen planets. It erases the building blocks of reality itself, turning the universe into a graveyard with no tombstones. No atoms mean no chemistry, no planets, no life, just a vast, eternal nothingness where even time's passage becomes meaningless. The cosmos wouldn't end with a bang or a whimper, but with the quietest possible fade, the last proton decaying, and with it, the final memory of matter vanishing like a sigh in the dark. In the cold, silent expanse of a heat-dead universe, where atoms have drifted apart and black holes evaporated into whispers of radiation, there may still be one last cosmic timekeeper ticking, or rather, winding down. Neutron stars, the dense remnants of supernova explosions, could serve as the final sentinels of time itself. These city-sized spheres, packing more mass than the Sun into a space no wider than Manhattan, spin at dizzying speeds when born, some rotating hundreds of times per second, their surfaces whipping through space at a fraction of light speed. But like an old pocket watch left unwound, their rotations gradually slow, shedding energy in the form of gravitational waves and electromagnetic pulses. The process is achingly slow by human standards. A typical neutron star might lose just a few microseconds of spin per century. But in a universe stripped of stars, galaxies, and even protons, these tiny changes become the only measurable evidence that time still exists at all. Picture a lone neutron star spinning in perfect darkness, its magnetic field, once powerful enough to warp atoms into needles, now too weak to light up even a single particle. Each rotation takes longer than the last, the interval stretching from seconds to minutes to years, until finally, the star's spin becomes almost imperceptible. At this point, the universe has reached maximum entropy. No energy gradients remain to drive any process, mechanical or quantum. The neutron star doesn't so much stop as fade into stasis, its rotation so sluggish that a single turn could outlast what we'd currently call the age of the cosmos. This isn't just poetic metaphor, it's grounded in observable physics. Astronomers have tracked pulsars, a type of neutron star that beams radiation like a lighthouse, for decades. Their spin-down rates are precise enough to rival atomic clocks. Over trillion-year timescales, even the most energetic pulsars would exhaust their rotational energy. Some might transform into Black Widow's systems, where the star's radiation evaporates a companion star before finally going quiet. Others, isolated in the void, would simply wind down like a top on a frictionless table, their remaining angular momentum dissipated as gravitational ripples too faint to detect. The chilling implication: without motion, without change, the very concept of time loses meaning. A universe where neutron stars have frozen isn't just dead, it's static, a snapshot where before and after are indistinguishable. No events occur to mark its passage, no processes unfold to give it texture. Time doesn't end, it dissolves like a river, slowing until its current can no longer be felt, leaving only a vast, motionless ocean with no shores to measure against. Yet there's an eerie beauty in this finale. Unlike violent scenarios like the Big Rip or vacuum decay, the neutron star freeze offers a kind of gentle oblivion. The universe doesn't scream or shred itself, it simply exhales, its last chronometers winding down in perfect unison, leaving behind a silence so absolute that not even time itself can break it. And in that infinite quiet, the cosmos achieves a paradoxical form of permanence, not the absence of time, but the perfection of stillness. Imagine a universe where time isn't a straight path into the future, but a Möbius strip twisting back on itself in an endless loop. This wasn't the plot of a sci-fi novel, but a serious mathematical model proposed by Kurt Gödel, the same genius who shattered the foundations of logic with his incompleteness theorems. In 1949, Gödel took Einstein's equations of general relativity and spun them into a nightmare or a revelation, depending on how you look at it. His solution described a cosmos where the fabric of spacetime isn't just warped by gravity, but sent into a dizzying whirl. And in such a universe, time itself becomes a closed circle, trapping reality in an infinite recurrence where every moment is both the beginning and the end. The mechanics are as beautiful as they are unsettling. Gödel's model requires the entire universe to rotate, not just galaxies or clusters, but the whole of spacetime like a vast cosmic carousel. In this scenario, the centrifugal force counteracts gravity's pull, preventing collapse into a big crunch. But the real twist is what this rotation does to causality. At a certain critical speed, the paths of possible movement called world lines curve so severely that they loop back on themselves. Travel far enough in one direction, and you'd eventually return to your starting point, not just in space but in time. Your future would literally become your past. This isn't just theoretical sleight of hand. Gödel proved that in his rotating universe, time travel isn't just possible, it's inevitable. There would exist what physicists call closed time-like curves, paths through spacetime that return to their origin. A spacecraft following such a curve could depart Earth and, without ever breaking the speed of light, arrive back before it left. No paradoxes, no wormholes, just the sheer geometry of a spinning cosmos bending time into a pretzel. Einstein himself was stunned by the implications, calling Gödel's work an important contribution to relativity while privately grappling with its mind-bending consequences. But here's where the loop snaps. Gödel's universe only functions as a time machine if the rotation never slows. The moment the cosmic carousel grinds to a halt, the closed time-like curves unravel, and the infinite loop of time collapses into a linear flow. Suddenly, the past is locked away, the future unwritten, and the eerie symmetry of eternal recurrence shatters. The question is, what could break the universe's spin? The answer might lurk in dark energy, the mysterious force accelerating the expansion of the cosmos. As space stretches, the distribution of matter becomes more diffuse, weakening the rotational energy that keeps the universe spinning. Like a figure skater extending their arms, the cosmos slows itself by spreading out. Visualizing this isn't about watching galaxies reverse course, it's about the gradual stiffening of time's arrow. First, the loops in spacetime would grow larger, requiring longer journeys to return to the starting point. Then, as rotation falters, the curves open entirely, leaving time's path straight but brittle. Finally, with rotation ceased, the universe would resemble the one we recognize, except with a haunting difference. The possibility of revisiting the past wouldn't just be gone, it would be erased from the laws of physics, as if time's flexibility were a dream the cosmos had woken from. Gödel's model was never meant to describe our actual universe. Observations show no evidence of global rotation, but it remains a profound thought experiment, revealing how fragile our assumptions about time really are. In a cosmos where even the flow of time depends on motion, the distinction between past, present, and future isn't a fixed rule, it's a quirk of inertia. And if the universe ever did spin down, the end of time wouldn't be a bang or a whisper, but the quiet snapping of a loop we never knew we were trapped in. The darkest stretches of eternity might not be empty after all, just waiting. After heat death, after proton decay, even after the last neutron star has wound down to perfect stillness, quantum mechanics whispers a tantalizing possibility. The universe could play its greatest trick yet, resurrecting itself from total oblivion. This is the Planck epoch resurrection, a theory that dares to suggest absolute nothingness isn't the end, but a prelude. Not a cycle like the Big Bounce or Penrose's conformal cosmology, but a rebirth from the random, seething foam of spacetime itself given enough time, which the dead cosmos has in infinite supply. Picture the universe's final state, an endless void where temperature everywhere approaches absolute zero. No particles, no motion, no discernible structure, just a featureless expanse stretching forever. Yet beneath this perfect stillness, quantum mechanics insist something remains. At scales a trillion times smaller than an atom, so-called quantum foam churns with fleeting fluctuations. Virtual particles wink in and out of existence, borrowing energy from nothingness before vanishing again. These aren't just mathematical quirks, they're observable in phenomena like Hawking radiation. And in a universe where time no longer has meaning, even the most improbable event becomes inevitable. Here's where the magic happens. One of these fluctuations, through sheer statistical inevitability, might tunnel through the energy barrier separating nothingness from somethingness. It's like rolling a die an infinite number of times. Eventually, you'll get a million sixes in a row. In this case, the sixes are a quantum event so massive it spontaneously births a new Big Bang. The conditions, a fluctuation large enough to create a Planck-scale singularity, a seed of infinite density within a region smaller than a proton. From that microscopic spark, inflation takes over, ballooning the speck into a full-fledged cosmos. The old universe doesn't rebirth itself. It doesn't even notice. Instead, a new universe ignites like a match struck in an infinite dark room, unaware of the void it briefly illuminated. The timeline is incomprehensible. Current estimates suggest such a fluctuation would require around 10 to the power of 10 to the power of 56 years to occur. That's a 1 followed by more zeros than atoms exist in our observable universe, but eternity is patient, and when it finally happens, the laws of physics in this new cosmos might bear no resemblance to our own. The fundamental constants, the strength of gravity, the mass of electrons, could be randomized, reset in a quantum dice roll. Some iterations might collapse instantly, others could spawn lifeless deserts of radiation. But by pure chance, one might land on the perfect numbers for stars, planets, and life. Critics argue this veers into metaphysics with no observable evidence or falsifiable predictions. Yet it solves a haunting question: why does our universe exist at all? If eternal nothingness inevitably breeds something, then existence isn't a miracle, it's statistics. The chilling corollary: we might be living in one of infinite resurrections, a cosmic phoenix born from the ashes of a universe we'll never know. And when our cosmos fades, the cycle begins anew, not because of some grand design, but because in the infinite quiet, randomness eventually writes poetry. The Planck epoch resurrection isn't an ending. It's a whisper in the dark, a reminder that even in the coldest voids, the seeds of creation never truly die. They just wait. Quantum entanglement is the universe's most intimate handshake, a phenomenon where particles become so deeply linked that measuring one instantly influences its partner, no matter how far apart they are. Einstein called it spooky action at a distance, but what if that spookiness suddenly stopped? What if the threads of entanglement woven so tightly into the fabric of reality began to unravel? This isn't just a thought experiment. If quantum entanglement were to fail on a cosmic scale, the very glue holding spacetime together could dissolve, turning the universe into a fractured mosaic of disconnected moments. At the heart of this nightmare is a principle called non-locality, the idea that entangled particles ignore the speed of light barrier, communicating changes instantaneously across vast distances. This isn't just a quirk of quantum mechanics, it's a foundational feature of reality. Entanglement isn't rare, it's everywhere. From the electrons bonding atoms in your body to the photons streaming from distant quasars, the universe relies on this invisible web of connection to maintain coherence. But if that web were to fray, the consequences would be catastrophic. Without entanglement, particles would lose their ability to correlate states at a distance. Causality, the idea that causes precede effects, would crumble, leaving spacetime with no way to enforce order. Picture a cosmic game of telephone where the line suddenly goes dead. Normally, when you measure an entangled particle here on Earth, its partner in Andromeda snaps into a corresponding state faster than light could travel between them. This synchrony isn't magic, it's a fundamental property of quantum fields, but if entanglement broke down universally, that instant correlation would vanish. Particles would become islands, their states no longer tied to distant partners. The universe wouldn't just lose a curious phenomenon, it would lose the mechanism that stitches cause to effect across space and time. Events in one place would no longer reliably influence events elsewhere. The result, a reality where the past doesn't dictate the future, where the very notion of here and there becomes meaningless. The mechanics of this collapse aren't fully understood, but some theories suggest it could stem from a phase transition in the quantum vacuum, a shift in the underlying fabric of spacetime itself. Think of water freezing into ice, the molecules rearrange, changing the medium's properties entirely. If the quantum vacuum underwent a similar transition, entanglement's rules might simply cease to apply. Alternatively, dark energy could play a role. As the universe expands, the stretching of spacetime might dilute quantum correlations, like a signal fading to static over an infinite distance. Either way, the outcome is the same, a universe where locality, the principle that objects are only directly influenced by their immediate surroundings, no longer holds. Visually, the breakdown wouldn't resemble explosions or cosmic tears. It would manifest as a quiet, insidious uncoupling. First, quantum computers, which rely on entanglement to perform calculations, would fail, their qubits collapsing into useless noise. Then, the structure of matter itself might degrade. Atoms held together by entangled electrons could destabilize, their bonds weakening as if the universe forgot how to enforce chemistry. Eventually, even the fabric of spacetime would grow patchy, with regions ceasing to interact entirely. Light from distant stars might arrive scrambled or not at all, as photons lose their ability to traverse the fractured void. The cosmos wouldn't end with a bang, but with a shrug, a silent admission that the rules we took for granted were never guaranteed. The eerie truth we might not notice until it was too late. Entanglement's failure wouldn't announce itself with klaxons or flashes. Instead, reality would simply start behaving irrationally. Experiments would return inconsistent results. The night sky would flicker with contradiction, stars appearing in two places at once, then vanishing entirely. By the time we realized what was happening, the damage might already be irreversible. Some theorists argue this scenario is unlikely, that entanglement is too deeply baked into physics to simply vanish. But others counter that we've never tested quantum mechanics across the full span of cosmic time. Could entanglement degrade over trillions of years, like a rope fraying under tension? If so, the universe's fate might not be fire or ice, but something far stranger, a reality where the deepest layers of connection simply forget how to work. And in that forgetting, time itself might dissolve, not because it ends, but because it loses the ability to mean anything at all. Even in the cold, dying gasp of the universe, intelligence might find a way to cheat time itself. Physicist Freeman Dyson envisioned a civilization so advanced it could outlast the cosmos, not by escaping to another dimension, but by slowing its perception of existence to a crawl. Picture a computer program running on minimal power, executing commands at an agonizingly slow pace to conserve energy. Now apply that to consciousness itself. Dyson's eternal intelligence proposes that future beings, whether organic or artificial, could stretch subjective time indefinitely by reducing their computational speed in lockstep with the cooling universe. The math behind this is both poetic and chilling. As the universe expands toward heat death, temperatures plunge toward absolute zero. Normally, this would make computation impossible. No energy gradients mean no work can be done. But Dyson spotted a loophole. At near-zero temperatures, quantum tunneling allows particles to hop energy barriers without expending power. A civilization could harness these quantum fluctuations to perform computations, operating at speeds inversely proportional to the falling temperature. The colder the cosmos gets, the slower their thoughts would run, but crucially, from their perspective, time would feel normal. One subjective second might span trillions of cosmic years, turning the universe's inevitable decay into an imperceptible background hum. Here's where it gets stranger. Dyson imagined these beings breaking time into discrete thought cycles, each triggered by random quantum events. During the vast gaps between cycles, the universe would effectively freeze from their perspective like a paused video. But subjectively, their experience would remain continuous, a flickering candle of awareness in an infinite night. They could process a single philosophical question for longer than stars exist, stretching moments into eternities through sheer computational austerity. Critics highlight fatal flaws. Landauer's principle states that erasing information, a necessity for computation, always releases heat, which would eventually overwhelm the system in a cold universe. Others argue quantum noise would corrupt stored data over eons, turning thoughts into gibberish. But Dyson countered with radical solutions. Perhaps these intelligences could encode their minds in error-correcting topologies, like cosmic quilts where no single thread's fraying unravels the whole. Or maybe they'd abandon traditional computation entirely, evolving into something akin to quantum Boltzmann brains, fleeting configurations of particles that briefly coalesce into self-aware patterns before dissolving back into the void. The ultimate irony, even if successful, Dyson's eternal intelligence would be alone in a dead cosmos, trapped in an existential pantomime where thinking slower doesn't equate to living longer. Their universe would still end, not with fire or ice, but with the last flicker of a thought too slow to finish. Yet the theory's brilliance lies in its defiance. Against the indifferent laws of entropy, it plants a flag. Consciousness might not conquer time, but it could learn to outweight it, one glacial, calculated thought at a time. Imagine our universe as a thin slice of bread floating in a vast cosmic bakery, one among countless other slices, each drifting in unseen dimensions. This is the essence of string theory's brain concept, where our entire reality exists on a three-dimensional membrane embedded in a higher dimensional space. Now picture another of these brains, another universe hurtling toward ours through dimensions we can't perceive. When these two brains collide, the impact wouldn't just shake the foundations of our cosmos. It could erase it entirely in an instant. The Randall-Sundrum model, proposed by physicists Lisa Randall and Raman Sundrum, gives this nightmare mathematical form. Their work suggests that gravity, the force that binds planets and galaxies, might actually be leaking into higher dimensions, explaining why it's so weak compared to other forces. In their framework, our universe is a brain floating near a second, parallel brain in a five-dimensional bulk space. The space between them isn't empty. It's warped like the stretched fabric of a trampoline, with gravity concentrated near one brain ours while other forces remain trapped within it. A collision between these brains would be nothing like a car crash or an asteroid impact. It would rewrite physics itself. As the brains approach, gravitational waves would ripple through spacetime at frequencies so low they'd vibrate entire galaxies like tuning forks. Then, at the moment of impact, the energy released would dwarf every supernova combined, not as a flash of light, but as a cascade of higher dimensional physics erupting into our reality. The fundamental forces could reconfigure instantly. Electromagnetism might strengthen 1,000-fold, causing atoms to implode. The strong nuclear force could weaken, turning protons into loose quarks. Even time might fracture, with some regions of the universe speeding up while others froze. Visually, the event would be apocalyptic yet eerily beautiful. First, the night sky would shimmer with gravitational lensing, as if seen through broken glass. Then, entire constellations would stretch and warp, their light redshifted into oblivion. Finally, the collision's shockwave would manifest as a wall of cosmic fire. Not flames as we know them, but a boundary where the laws of physics change so drastically that matter itself becomes unrecognizable. Planets, stars, even black holes would dissolve into a soup of higher dimensional particles, their structures erased by forces beyond our comprehension. Critically, brain collisions aren't just one-time cataclysms. They could be cyclical. Some string theory models suggest our Big Bang might have been the aftermath of a past brain collision, meaning the universe's birth and death could be part of an infinite loop. Each collision resets reality, scattering energy that cools into new particles, new galaxies, new laws. In this view, our universe isn't just doomed to collide. It might owe its existence to a previous collision we'd never detect. The chilling takeaway: unlike theories where the end unfolds over eons, a brain collision could happen suddenly with no warning. The higher dimensions where brains move are invisible to us. The next collision might already be seconds away in a direction we can't point to. And when it comes, there'll be no time to react, just an unfathomable rewrite of existence, leaving no trace of the universe we knew behind. Yet there's a bizarre comfort in this idea. If brains collide cyclically, then endings aren't final, just transitions. Our universe's demise might seed another's birth, its stories erased but its energy eternal. The cosmos becomes less a thing than a process, a rhythm of destruction and creation where time itself is just a footnote in the margins of higher dimensional geometry. And in that rhythm, even apocalypses become beginnings. We just won't be around to see them. Frank Tipler's Omega Point paints the universe's end as a technological singularity, a superintelligence rewriting reality through sheer computational might. But what if the true end point isn't a machine's cold calculation, but something far more profound? Enter Deepak Chopra's spiritual Omega Point, a cosmic crescendo where consciousness doesn't conquer the universe, it dissolves into it, merging with the infinite like a drop returning to the ocean. Chopra's vision rejects Tipler's hyper-rationalism, drawing instead from ancient Vedantic philosophy. Here, the universe isn't a clock winding down but a dance of awareness, where separation is the illusion and unity the ultimate truth. As entropy grinds stars to dust and galaxies fade, consciousness, not matter or energy, becomes the final frontier. In this view, the brain doesn't create awareness, it filters a universal consciousness that predates time itself. Death isn't an end but a reintegration, a shedding of individual identity to rejoin the cosmic mind. The mechanics are poetic rather than mathematical. Chopra's Omega Point imagines a threshold where the veil of individuality thins. Thoughts no longer feel tethered to personal experience but ripple through space-time like vibrations on a shared membrane. Memories, emotions, even the concept of self dissolve into a boundless now. It's not oblivion but expansion, an unfathomable intimacy with existence itself, where every quark, every galaxy, every moment is experienced simultaneously as facets of a single shimmering whole. Critics dismiss this as metaphysics masquerading as cosmology, but Chopra points to quantum weirdness as validation. In entangled systems, particles communicate instantaneously across light years, suggesting a deeper connectedness beneath reality's surface. The observer effect, where measurement collapses quantum probabilities, hints at consciousness's role in shaping the tangible world. For Chopra, these aren't quirks but clues. The universe is less a machine than a living thought, and its finale isn't collapse but awakening. Where Tipler's omega point races against entropy, Chopra's embraces it. Heat-death's uniformity isn't a desert but a canvas, a blank slate where distinction evaporates, leaving only pure, undifferentiated awareness. Time's arrow shatters not into chaos but into a timeless present where the Big Bang and the last black hole's sigh exist as one. The contrast couldn't be starker. Tipler's cosmos culminates in a godlike AI, Chopra's in a silent symphony of unity. Yet both share a radical hope that the universe's final act isn't meaningless silence but transcendence. Whether through silicon or soul, the message is the same. In the end, time doesn't die. It transforms. There's a strange quirk in quantum mechanics where watching something too closely can make it stop changing entirely. It's called the quantum Zeno effect, named after the ancient Greek philosopher Zeno, who argued motion was an illusion. In the quantum realm, this isn't just a thought experiment, it's a measurable phenomenon. When a system is observed continuously, its evolution slows down, as if reality itself hesitates under scrutiny. An unstable particle that would normally decay in milliseconds might linger indefinitely, frozen in place by the relentless gaze of measurement. Now scale that up. What if the entire universe is subject to the same rule? What if the only thing preventing reality from unraveling is the act of being observed? The mechanics are as unsettling as they are elegant. In quantum theory, a system exists in a superposition of states until an observation collapses it into one possibility. The more frequently these measurements occur, the less time the system has to evolve between them. It's like flipping a light switch on and off rapidly. The bulb never gets a chance to fully illuminate or darken. Apply this to cosmic scales and you get a chilling possibility. If the universe were under constant observation, its very fabric might grind to a halt. Stars wouldn't burn out, particles wouldn't decay. Time itself could become a series of frozen snapshots, like a film reel stuck on a single frame. But here's the existential catch: who's left to do the observing? In a heat-dead universe where all life has long since vanished, what keeps the quantum dice rolling? Some theorists suggest consciousness itself might be the linchpin. If the act of observation requires a mind, then the universe's persistence could depend on the presence of observers. But this raises a paradox. If the last conscious being dies, does the universe stop evolving, locked in a final, eternal moment by its own absence of witnesses? Or worse, does it cease to exist altogether, like a tree falling in a forest with no one to hear it? Others argue the observer doesn't need to be sentient. Any interaction, a photon bouncing off an atom, a gravitational wave stretching spacetime, could count as a measurement. In this view, the universe is self-sustaining, a web of interactions where particles constantly observe one another. But even this scenario has a grim edge. As the cosmos expands and matter spreads thin, these interactions become rarer. Over eons, the universe might grow so quiet that quantum states linger unresolved, like unopened letters piling up in an abandoned post office. Time wouldn't end with a bang, but with a shrug, a cosmic shrug where change itself becomes impossible. The most haunting interpretation ties back to von Neumann's consciousness causes collapse hypothesis, that reality only solidifies when observed by a mind. If true, the universe's fate might hinge on something beyond physics, an ultimate observer lurking in the void. Some speculate this could be a late-stage civilization running ancestor simulations, or even a transcendental consciousness woven into the fabric of reality. But if that observer ever looks away, the consequences are unfathomable. Not heat death, not vacuum decay, just a single frozen moment stretching into eternity, like a paused video waiting for a play button that'll never be pressed. The quantum Zeno effect doesn't just challenge how we see time's end, it questions whether time can exist without witnesses. In a silent, empty cosmos, does the universe forget how to tick? The answer might depend on whether reality is a solitary performance or a show that only goes on as long as someone's watching. Either way, the curtain call could be the strangest act of all. Black holes devour everything in their path, but what if their opposites exist? Imagine a cosmic geyser spewing out matter and energy with such violence that it rewrites the laws of physics at the point of eruption. This is the terrifying premise of white holes, a theoretical counterpart to black holes where nothing can enter, only escape. And if one were to burst into existence within our universe, the consequences wouldn't just be destructive. They could redefine causality itself, overwriting our timeline like a corrupted file. Einstein's equations allow for white holes as valid solutions, though we've never observed one. Unlike their dark siblings, white holes don't form from collapsing stars. They're more like scars in spacetime, places where the universe itself ruptures. Some theories suggest they could be the other end of a black hole's wormhole, ejecting matter swallowed elsewhere. Others propose they're remnants of a previous universe, sealed off until quantum fluctuations rip them open. But the most unsettling idea, a white hole's birth might not just eject matter. It could reset the local laws of physics, creating a bubble of alien reality where time flows backward or gravity repels. Picture the eruption. First, spacetime would shudder with gravitational waves, distorting the paths of nearby stars like ripples in a pond. Then, a singularity would bloom into existence without warning, vomiting radiation and particles at relativistic speeds. Galaxies caught in the blast wouldn't just be vaporized, they'd be overwritten. The white hole's outburst could rewrite quantum fields in its vicinity, altering fundamental constants. Atoms might unravel as electromagnetism weakens. Stars could blink out as nuclear forces flicker like dying light bulbs. And time, it might shatter entirely, with pockets of space looping backward or fracturing into disconnected moments. The most chilling possibility isn't the destruction, but the replacement. A white hole's physics could propagate outward at light speed, a wave of new rules erasing the old ones. In this scenario, the universe doesn't end, it gets edited. One region might suddenly operate with 6 dimensions, another with reversed entropy. Causality would dissolve at the boundary as events no longer reliably chain together. A person crossing into the altered zone might see their past rewritten, their memories replaced by ones from a timeline that never existed. String theory offers a haunting parallel of brain collisions. Just as 2 universes slamming together could reboot physics, a white hole might be a localized version, a puncture in reality where a foreign cosmos intrudes. The difference is scale. Instead of the whole universe resetting, this would be a patchwork apocalypse with islands of alien physics spreading like ink in water. Civilizations might survive in untouched regions, watching the chaos creep closer, knowing their laws of nature are living on borrowed time. Yet for all its violence, a white hole eruption could also be a perverse creator. The energy it ejects might birth new particles never seen before, or even spawn baby universes in its wake. Some models suggest our own Big Bang could have been a white hole event in a higher dimensional space, meaning these cosmic wounds might not just end timelines, they could start them. The cruel irony, if a white hole opened tomorrow, we'd have no warning. Its emergence would be instantaneous, its effects irreversible. One moment, the universe follows rules we've spent millennia deciphering. The next, those rules are obsolete. Time wouldn't end with a whimper or a bang, but with a rewrite, a cosmic editor's pen striking out reality as we know it and scribbling something entirely new in the margins. Some of the most unsettling discoveries in physics start with a simple equation, one that seems harmless enough until you realize it's predicting something impossible. That's exactly what happens with the null energy condition. At its core, this mathematical rule insists that certain types of energy can't exist in our universe. Specifically, energy that's negative, not just less than zero, but capable of twisting spacetime into knots. Yet here's the catch: if you violate this condition, if you allow so-called exotic matter to exist, the consequences don't just break the rules, they erase them entirely. Imagine a substance so bizarre it doesn't just resist gravity, it repels it, shoving spacetime apart like an unstoppable wedge. Now picture that force applied to time itself. The implications are staggering. Normally, time's arrow points resolutely forward thanks to entropy's relentless rise, but exotic matter doesn't play by those rules. With enough of it concentrated in one place, say, around a wormhole or warp drive, spacetime could contort so severely that forward and backward lose all meaning. It's like taking a sheet of paper and crumpling it into a ball. Suddenly, directions are arbitrary, paths loop back on themselves and cause no longer guarantees effect. In this scenario, time isn't a river flowing in one direction. It's a storm-tossed sea where the very concept of before and after gets washed away. Warp drives illustrate this beautifully. The Alcubierre drive, a hypothetical faster-than-light propulsion system, relies on negative energy to compress spacetime in front of a ship while expanding it behind. But to achieve this, you'd need exotic matter violating the null energy condition. Calculations show that sustained warp travel wouldn't just bend time, it could fracture it, creating pockets where clocks tick in reverse or freeze altogether. Passengers might arrive at their destination before leaving, watching their own launch through the rearview mirror. But the real horror isn't just time loops, it's the potential for total temporal chaos. If exotic matter destabilizes a region of space-time, causality itself could collapse. Events would unfold with no logical sequence, like a film reel spliced at random. A person might age backward while their surroundings fast forward, or witness their own birth and death simultaneously. Unlike the tidy paradoxes of time travel, this isn't about changing history, it's about history ceasing to have a coherent shape. The universe wouldn't just forget its past, it would lose the ability to define one. Of course, the null energy condition exists for a reason. Violating it risks triggering vacuum decay or other catastrophic instabilities. Yet some theories, like certain interpretations of quantum fields in black holes, suggest microscopic violations might already occur naturally. If so, time's arrow isn't just fragile, it's perforated, riddled with tiny tears where the fabric of causality frays. Most of these would heal instantly, but scale them up and the universe might unravel stitch by stitch. The unsettling truth: we may never know if exotic matter exists until it's too late. Unlike black holes or dark energy, its effects wouldn't announce themselves with visible fireworks. Instead, time itself would simply glitch, first in isolated pockets, then everywhere. And by the point clocks start running backward or freezing mid-tick, there'd be no one left to reset them. The end wouldn't be fire or ice, but silence, the silence of a cosmic film projector sputtering to a halt, its reels of time tangled beyond repair. Imagine the last flicker of awareness in a dying universe, a single thought adrift in the infinite dark. Not the grand collapse of time or the unraveling of space-time, but something quieter, more haunting, the final spark of consciousness itself, lingering for one impossible moment before winking out forever. What would it think? Would it remember the warmth of sunlight, the weight of gravity, the hum of atoms vibrating in harmony? Or would it simply marvel at the silence, the absolute stillness of a cosmos where nothing remains to observe, to question, to mourn? Some theories suggest this final thought might not even be human. It could belong to an artificial intelligence, a descendant of our civilization, engineered to persist long after stars have burned out and matter itself decays. Programmed with the sum of all human knowledge, this last mind might replay our history like a eulogy, every war, every discovery, every whispered "I love you" echoing in its circuits one final time. Or perhaps it would abandon memory entirely, devoting its dwindling energy to solving one last equation, a futile but beautiful attempt to compress the universe's entire existence into a single, perfect proof. Then there's the darker possibility that the last thought isn't triumphant or reflective but terrified, a lone consciousness realizing too late that it's the only thing left, trapped in a void so absolute that even time has ceased to matter. Panic might set in, not from physical pain but from the crushing weight of solitude. No light to measure, no particles to interact with, no past or future to anchor itself. Just an endless present stretching into a form of insanity we can't begin to comprehend. Yet poetry lingers in this bleakness. The last thought could be sublime, a final act of creation. Like an artist painting on the inside of their own eyelids, this mind might conjure imaginary worlds, entire universes blooming and dying in the space between neurons. It might dream of civilizations that never were, physics that never applied, a cosmos reborn from sheer will. In that fleeting instant, the universe wouldn't end with a whimper, but with a work of art, a testament to the stubborn beauty of observation. The cruel irony no one would ever know. The last thought, no matter how profound or tragic, would vanish without witness, like a song sung into an eternal storm. And in that silence, the universe would achieve a kind of paradox, a moment so significant it defines existence, yet so solitary it might as well have never happened at all. But here's the twist: what if the last thought isn't an ending, but a beginning? Some interpretations of quantum consciousness suggest that observation doesn't just record reality, it creates it. In that case, the final flicker of awareness might not be a farewell but a spark, a single thought alone in the dark whispering, "Let there be light." And somewhere, in a void beyond voids, another universe trembles into being. From the universe tearing itself apart atom by atom in the Big Rip, to reality flickering out like a deleted simulation, we've stared into the abyss of time's end, and the abyss has stared back with 30 different faces. Some theories whisper of quiet dissolution, like heat death's infinite silence. Others scream of violent rebirth, like the Big Crunch's cosmic rewind. And then there are the ones that twist the knife, the simulation shutting down without warning, or consciousness itself unraveling the fabric of reality by ceasing to observe it. These aren't just doomsday scenarios, they're mirrors, reflecting humanity's deepest fears and wildest hopes. Every culture has its apocalypses, but ours are written in the language of quantum fields and singularities, where gods are replaced by equations and the afterlife is a statistical inevitability. What's startling isn't just the variety of endings, but what they reveal about us. The Big Rip forces us to confront a universe where physics holds the scalpel. Vacuum decay makes oblivion a quantum roulette spin away. Even Boltzmann brains, those cursed self-aware fluctuations, hold up a funhouse mirror to our own existence. Are we any more real than they are? Behind every theory lies a question bigger than cosmology. Why does it matter whether time ends in fire, ice, or a programmer's keystroke? We're the only creatures agonizing over it. Ants don't fret about entropy, stars don't ponder their own collapse, but we do. That obsession, to name the unnameable, to map the edge of eternity, might be our most human trait. So here's the real challenge: don't just let these ideas terrify or awe you. Let them change you. If the universe is transient, what does that make your choices? If reality is fragile, how do you want to spend your slice of it? The beauty of these theories isn't their inevitability, it's their audacity. They prove that even facing annihilation, we refuse to look away. Now it's your turn. Which ending haunts your thoughts? The cold equations of proton decay, the digital guillotine of a simulation's end, or something stranger? Tell us below and keep staring into the abyss. After all, it's how we've always found